Let's get going. Well, it's a great pleasure to introduce the first speaker, particularly because I'm not the first speaker. That's Dave Benson from fellow Aberdonian, the signature mod 8 of surface bundles and the cohomology of finite groups.
Thank you. Well, it's a great pleasure to be invited to Oberwolfach. I'm the other Benson. Benson apparently wants to write a joint paper with me just because of the way the author list would work. So I told him that that's fine, but we should use first names. Anyway, so
you have to act there.
Yeah, so yes, what was it? Yes, I'm really here as part of the minority program. So there really aren't enough finite group theorists here, so I'm going to tell you a story about some work I've been doing with these three authors about how to compute the signature of a surface bundle modulo 8 using cohomology of finite groups and representation theory of finite groups. So this is a story that started earlier this year. And it's sort of not what I usually do, so you'll bear with me if I sort of introduce things a bit slowly. So anyway, let's have the usual thing, which is a surface bundle. And I understand there are two different conventions as to which is G and which is H. This is the one I'm going to use. So associated with this, there's a map from pi1 of sigma H to the mapping class group of genus G, which is just the diffeo plus of this modulo isotopy. And then there's an obvious map of this to symplectic 2G of Z, or of Z, whichever you prefer. And we're going to call the composite of these two maps chi. And we have a theorem of Meyer from 1973, which tells you how to compute the signature of M. And he defined a 2 cycle on the symplectic group. And what he proved was that the signature of the manifold M is just the evaluation of, well, you take the cohomology class defined by tau, and you chase it back through chi to give a cohomology class on pi1. Now, the cohomology of pi1 of sigma H has a canonical degree 2 element, which is just the fundamental class of that manifold. And so we evaluate on that homology, degree 2 homology class, sigma H. And he noted that this is divisible by 4. Okay, so you probably all know this already. Let me just recall what this cohomology class looks like. This talk is going to follow on very well from Benson's talk a couple of days ago, because we're basically taking the same co-cycle and chasing it right round to some finite groups. So let's just recall that pi1 of sp2gr is Z. So if I take this Lie group, its universal cover is just a Z-fold cover. And as with any Lie group, the universal cover is again a Lie group. So this is a Lie group. I should warn you, it doesn't actually have any faithful finite dimensional representation, so it's a bit of a peculiar Lie group. But inside here, if I pull back this extension to SP2GZ, let's call this cover that we get that way SP2GZ tilde. This, at least if G is at least 4, this is the universal central extension. For G equals 1 and 2, there is no universal central extension because this isn't a perfect group. For G equals 3, there's an extra Z mod 2 in the universal central extension, so we don't want to talk about that Z mod 2. It comes from the finite symplectic group SP6 of Z mod 2. There's an exceptional double cover there. So anyway, if I take this element of H upper 2 of this group, this tau is actually 4 times this class. So let me just write tau represents 4 times this extension. And that actually explains in some sense the divisibility of this quantity by 4. So this is all very classical. And then there's a theorem of Deline which gives you some sort of limitation on how much of this cover you can see on finite quotients of this symplectic group. So this theorem of Deline, all the theorems I'm going to be quoting are from the 1970s, by the way. This work could have all been done ages ago. This theorem is from 1978. So he proved that SP2GZ tilde is not residually finite. To be more precise, what he proved is that every subgroup of finite index contains twice this central element here. So every subgroup of finite index contains 2Z. So there's a subgroup of this centre. The full centre of this, actually, I should explain, is twice as big as Z. It's either Z cross Z mod 2 or Z according to the parity of G. But it's twice as big as this Z in both cases. Where are we? Okay, so in some sense, this theorem tells you as a consequence that if we use cocycles on finite quotients of SP2GZ, at best, we can only compute the signature mod 8. And that's precisely what we will do. And so here's how you do it. You ready? So let's set up a little bit of notation first. So I'm going to write J for the standard symplectic form. and SP2GZ is the set of matrices X satisfying X transpose J, X equals J, the usual thing. And I'm going to write gamma of n for the matrices in SP2GZ congruent to the identity mod n. So this is the principal congruence subgroup of level n. And now I'm going to give you a definition of a subgroup of this SP2GZ of finite index, which is going to give us a quotient of interest to us. This subgroup is going to be K. So this is the subgroup of SP2GZ consisting of the matrices of the form I plus 2A, 2B, 2C, I plus 2D. So they're in gamma of 2, but such that the diagonal elements of B and the diagonal elements of C are divisible by 2, and the trace of A is also divisible by 2, which is actually the same as saying that the determinant of 1 plus 2A is divisible by 4. So, if you think about it, gamma of 4 is contained in K, is contained in gamma of 2. Alright? And the index in gamma of 2 of K is, well, we got G diagonal elements of B, G diagonal elements of C, and one more for the trace. So it's 2 to the 1 plus 2G. Okay? And notice that, so that's this index. This index is much larger because the index in gamma 2 of gamma 4 is quadratic in here. So I'm quotienting out most of gamma 2 modulo gamma 4, as it were.
Is it easy to characterize in geometric terms what it is stabilizing? It's something in the Z mod 4 reduction of the symplectic lattice, right? So
yeah. I think I'll choose not to answer that question if you don't mind. It does stabilize something. It's actually quite complicated to describe. Yeah. So let me write down a theorem which says some of the properties of this K. The first interesting, so this is what we've been doing. So the first part, well, I mean, this is not that hard. K is normal in the symplectic group. So, in particular, if you think about K, it sits in a short exact sequence. So the quotient by K sits in a short exact sequence like that. And this sequence does not split. That will be important later on.
You should just say that the middle map maps to SP2GZ4 from S. Just there's an error from or to SP2GZ4. Isn't there? Two, I think.
There's a map
Oh,
SP2G Z14 to here. Is what you're
That's very
saying.
important.
Yes. So this is a quotient of SP2G Z14.
That's right.
Yes. Okay, good. Yes. Yes. Glad to have co-authors in the audience.
I'm trying to find out what the theorem is.
Yeah, so those are the first two parts of the theorem. This has the theorem of many parts.
Yeah, many parts.
So the third part says what the action of this on that is. So this is a 2G plus 1 dimensional representation of this group. So it turns out that the action of SP2G Z mod 2 on Z mod 2 to the 2G plus 1 illustrates the isomorphism between SP2G Z mod 2 and the orthogonal group in dimension 2G plus 1. So this is something exceptional and characteristic too. The B-end Dinkin diagram and the C-end Dinkin diagram are the same in characteristic too. Part 4.
What does it mean to illustrate the isomorphism?
Well, I mean, you've got a map from here to the automorphism group of this. It fixes a quadratic form, and so you get a map from the symplectic group to the orthogonal group of that quadratic form. That is this isomorphism.
Well, it actually defines, it doesn't illustrate, it defines.
Picky. For G at least 4, we can actually compute H2 of SP2GZ mod K. Well, we can compute it for all G, it's just in low genus there are some exceptional things that happen and I don't want to go into that. But usually you just get Z mod 2. And I'll actually explain why that is. But, I mean, even for G at least 2, there exists a non-zero element of this H2, which inflates to, if you think about a quarter of Meyer's class, and then reduce it mod 2, so this is as an element of H2 of the symplectic group with Z mod 2 coefficients. So there's a map from SP2GZ to this group, and I just...
inflation is other word for pullback.
Yes.
Yeah, it's the normal group cohomology word for pullback. That's it.
Yeah.
Yeah. One of the important things about this extension is what it does on gamma of 2 mod k. There you get something called an almost extra special group, which is the key to understanding the whole thing somehow. So restricting, or pulling back, as some people say, the extension of SP2G Z mod K by Z mod 2, defined by this class, to gamma of 2 modulo K, which is this group Z mod 2 to the 2G plus 1, gives an extension. So Z 1 goes to Z mod 2, goes to, I'll call it E, goes to Z mod 2, to the 2G plus 1 goes to 1, where E is an almost extra special group. And I'll explain what that means. So this is order 2 to the 2G plus 2 now. So these things have long been studied by finite group theorists, and in fact there's a paper of Bob Grice from 1973 that's going to be crucial to us in understanding that. But first of all, let me point out a theorem of Dempwolf.
So this gamma 2 mod k is Z2 to the 2G plus 1, is that right?
Yes, that's gamma of 2 mod k, right there. This is also from the 1970s. So it turns out that for G at least 2, the degree 2 cohomology of SP 2G Z mod 2 with coefficients in this natural symplectic module, Z mod 2 to the 2G, there's a unique non-split extension, is really what this is saying. So if I take the extension, this extension, and mod out there's a Z mod 2 in the bottom of this. If I mod it out, I get the unique extension that Dempwolf had in his theorem.
Is this Z2 mod 2 to the power T 2G plus 1? Is that something like the space of affine forms on the space of Arfin variance? There's an affine space, right, of dimension.
Yeah, I think that's exactly right. Yeah. Part of this holds a non-singular quadratic form,
Right.
but which is a non-degenerate quadratic form, which is singular in the sense that it has a null vector for the associated bilinear form. And if you mod that out, you get the symplectic space. So that one-dimensional something here is just this trace condition. Is that making sense? Yeah. Okay, so now I need to tell you about extra special and almost extra special groups.
Can I just start with geometric? Point is this is a very new way of understanding the examples of Maya of surface balance of signature form.
Yes, exactly.
So that's just the deep algebraic reasons for why they exist. Surface balance of signature form.
Yeah, yes, if you like.
Can you say once more what this last theorem, how this last theorem fits in?
This theorem fits in. So if I take this extension and mod out the Z mod 2 at the bottom of this, there's a unique central Z mod 2 in this whole thing. So I get an extension which is Z mod 2 to the 2G, which is the symplectic space now. So some group goes to symplectic 2G, Z mod 2 goes to 1. This is non-split, and so it has to be the same as any other non-split extension. And we're going to produce another non-split extension. Okay, so let's just recall what the cohomology of elementary abelian 2 groups looks like. This is just a polynomial ring in some classes which I've chosen to call Z1 up to Zn. So the Zi are in H1 of Z mod 2 to the n z mod 2, which is the same as hom z mod 2 to the n z mod 2. So the z's form a basis for the linear dual of this elementary abelian group. And so what is a degree 2 element? It's a quadratic form on the group. So H2 equals quadratic forms on Z mod 2 to the n. And how does that work in terms of group extensions? Well, so what does quadratic form mean? It means that Q of x plus y is Q of x plus Q of y plus B of xy, where B is symmetric bilinear. So Q and B tell you the square and commutator map. So in other words, if I take the corresponding group extension, and I take some elements x and y here, and lift them up to E in any way you like, call the lifts x hat and y hat, then x hat squared is of course well defined. It doesn't depend which pre-image I take, and that's just Q of x as an element of Z mod 2, this centre. And x hat comma y hat, the commutator, is just B of xy. So the quadratic form given by the element of H2 just explicitly tells you the squares and commutators in this group. How do I rub things out? Is it this?
Yes.
Good. So let me tell you about the classification. So for non-singular quadratic forms, you have to have an even dimension, so n is even. And there's two types depending on the Arf invariant, which is either 0 or 1. And Arf invariant 0 gives what's called the extra special group, n is 2g here, of plus type, and 1 gives the extra special group of minus type. So there are two types of extra special group corresponding to the two possible Arf invariants. And if you look at things which are non-degenerate but singular, in other words, the quadratic form is non-degenerate but the bilinear form may have a kernel, then there's only, well, n is odd in this case, and there's only one type. So this is 2 to the 1 plus 2g plus 1, so that. An extra special group like that. Oh, so these are called extra special. And these are called almost extra special.
Can you say again what is non-degenerate but singular?
So non-degenerate means the
As
Q inverse
could
of
be?
0 intersect B per is 0. It is non-degenerate. And non-singular just means that B perp is 0.
I don't know if it's not going to play a role, then forget it, but if it is, I know it, but can you define R from here? But Alan Reed doesn't know it, so.
I'm not going to need it. I'm actually not going to need it, so ignore it.
Okay.
I just wanted to fill in a bit of background on extra special groups.
Okay, good.
Yeah. Yeah, Andrew knows.
And I'll tell you later. Not this time. Not
Okay, so
limited time left.
we really have a limited time left, so I've got to get a move on, unfortunately. But so I need next to describe automorphism group of an extra special group. And I'll just do this in the almost extra special case because that's the one that we're interested in here. In almost extra special case. So the inner automorphisms are just the extra special group modulo its centre, which in this case just has order 2 to the 2g. And the quotient is actually the automorphisms of this orthogonal form, which is the symplectic group of one lower dimension, symplectic 2g z mod 2. But there's an extra z mod 2 because you can actually, the centre of this group is cyclic of order 4 and you can just invert it. And we actually want to ignore this extra z mod 2 because it doesn't feature. So we're going to look at the index 2 subgroup in here. So we're going to look at actually order the derived group just mapped onto symplectic 2g z mod 2. And this is non-split. So we look back at Dent-Wolf's theorem and we say this must be then the unique non-split extension. And so it's the same as the one we got from this by modding out the centre, which gives us a clue as to how to build a central extension of sp2g z mod k. Because that's where the theorem of Grice comes in. This is Grice, 1973. And I'm going to assume G is at least 3. So there is a group extension. One goes to E, goes to G, goes to SP, 2G, Z mod 2, goes to 1, fitting together this extra special group and the automorphism group. I mean, this didn't have to happen. The reason why this happens is representation theory, basically. So the properties here are that G modulo the centre of G here is just the derived group of the automorphism group of E, and the largest normal 2 subgroup of G is just E. So somehow the outer automorphisms fit together with the group to make an extension.
Can you say again what is O2? You said it, but just repeat it. What O2?
O2 means the largest normal 2 subgroup.
No, just normal 2.
Largest normal 2 subgroup in G is E. So by Dent-Wolf's theorem, we have that G modulo the central element of order 2. The Z mod 2 at the bottom of E is isomorphic to SP 2G Z mod K. So this comes from Dent-Wolf. It's just the uniqueness of the extension. We've just got 2 different groups which are extensions in the same way. So in particular, that tells us that H2 of SP 2G Z mod K with Z mod 2 coefficients has a non-trivial element given by this group. So is non-zero. So we've got a lower bound. There's at least a non-zero element here. So how do we form an upper bound? Well, we can just use the 5-term sequence in group cohomology to give an upper bound on this. So this chalk is going into ever smaller pieces, but H2 of SP2G Z mod K, Z mod 2, to H2 SP2G Z mod 2, which we know is injective. And the proof goes, well, you use the 5-term sequence in group cohomology, so you just have to compute H0 of SP2G Z mod K with coefficients in H1 of K Z mod 2. And this is an easy group theoretic computation, and you get 0. It basically says everything in K is generated by commutators of things in the symplectic group with things in K. So, this together with that actually compute H2 of this group, because this is Z mod 2. At least for genus, at least 4 or something. So how do we understand this group G that we've built here? That's where the cohomology class is coming from. Well, let's write down a representation. So I'm going to give you a map from SP2GZ mod K to the unitary group over the complex numbers in dimension 2 to the G mod plus or minus 1. And then lifting back over this plus or minus 1 gives you the extension. So this is just building a representation of that dimension. And actually it's still irreducible on E. And the way you obtain this representation is basically you build it on E and then extend it. So I'm just going to write down some matrices for you. So the basis of this 2 to the G dimensional space is for each W in Z mod 2 to the G, I'm going to write a basis element E sub W. So this matrix sends E sub W just to I to the power of W transpose B W E sub W. Now why is this well defined? So these are 4th roots of unity, and B, if you think about what's left of B in this group, the off-diagonal elements of B are defined mod 2, and the diagonal elements are defined mod 4. So it's really a quadratic form from Z mod 2 to the G to Z mod 4. And so it's well defined. A00A star means transpose inverse, sends EW to square root of determinant of A, and I'll tell you what that means, E sub A star W. So the determinant of A is either plus or minus 1 in Z mod 4, and the square root means you take either plus or minus 1 if it's plus 1, or plus or minus I if it's minus 1. So this is in 1I minus 1 minus I, but I'm only giving it up to multiplication by plus or minus 1. And then all I need to do now is to tell you where 0I minus I0 goes to. That sends EW to the sum, to 1 over 1 minus I to the G times the sum over W prime of minus 1 to the W transpose W prime. So just the inner product there, E sub W prime. So that's a matrix of plus or minus 1s divided by this constant. And that's a representation.
What is the constant?
1 over 1 minus I to the power of G. Shall I swap the boards? Okay, so in the last 3 minutes I'm going to give you a recipe for computing the genus. Modulo 8. Signature, modulo 8, sorry. We're losing language here. Yes. Okay, so we have our map from pi 1 of sigma h, so gamma g, and then we composed it to sp2g z. Now we're going to quotient out k and then go to u2 to the g modulo plus or minus 1, this representation by matrices. And so let's call that composite phi. This group is generated by sort of elements A1, B1 up to AH, BH, with one relation. It just says A1, comma, B1 up to AH, comma, BH is the identity. So what do we do? Each phi of AI, comma, phi of BI phi of AI and phi of BI were only defined up to multiplication by plus or minus 1, but if you take their commutator, each thing occurs twice, so the signs cancel out. So it's actually well defined in u of 2 to the g. And if I take the product of these things, the product was supposed to go to 1 in the quotient group, but the answer has to be either plus or minus the identity element here. And plus the identity if sigma of m is congruent to 0, minus the identity if sigma of m is congruent to the answer. And that looks like a good point to stop. There's your recipe. Thank you.
Any questions for Dave?
Yes.
So in the event that the signature is divisible by 8, is there any hope of getting some sort of secondary invariant that can tell you about like further divisibility?
Not from finite quotients. I mean,
K to Z.
sorry?
You need K, algebraic K theory, K to Z.
Yeah.
K to that.
Yeah, the finite quotients really can only ever tell you the signature modulo x is the upshot of Deline's theorem.
Right.
I have a question. It relates to the Torelli group. If you're in the Torelli group, but everything is 0 here, this is the orthogonal story, but this is looking to me, all the objects you're dealing with are in the work of Dennis Johnson that computes the mod 2 cohomology of the Torelli group. It's like Boolean algebra of
So
somehow it feels like you're sort of detecting stuff in the Torelli group.
you actually don't detect anything in the Torelli group here, and the reason is so. What's the name of your student who?
Korzeniewski.
Korzeniewski proved, and I actually, as of last night, have a new proof that if the image of this map into symplectic 2G Z mod 2 is trivial, then the signature is divisible by 8. So the Torelli group just vanishes that.
I mean, any bundle with monodromy in the Torelli group is virtually a product. That's not
Yes, quite.
Right,
Yeah.
right. That's not what I'm saying. I'm saying that like somehow, yeah. So that's definitely true. That's what I'm saying.
Yeah.
So the Torelli group thing is trivial, but somehow, like all the, I guess my question was, is that all these kind of mod 2 invariant. This is like the story when you compute the abelianization of the Torelli group. And what I'm trying to say is, when you have something non-zero signature, okay, like you have the monodromy, you can start messing with the monodromy. In other words, you're not completely. Okay, maybe I don't have a fully formed idea. I'll just say this: it's a question. If you haven't looked at it, and if you haven't, then you should look at it. the story of Dennis Johnson doing it's all the same objects. Like computing the abelianization of the Torelli group with mod 2 coefficients, and it involves the Roquelin invariant and all. So I don't know, it just,
Does he use Deline's? I'm sorry, does he use extra special groups? Finite.
no, he doesn't. No. Oh, I'm not saying this is known or
What do you mean
anything.
by the same?
You know, sorry. Maybe we should talk after. I just want to say, no, I'm not saying like, oh, he knew that. I'm just saying it feels like there's like a
Connection.
something that maybe right connection.
Sure, there's a connection. We will talk about
Yeah,
that.
like probing some next level
Yeah.
signatures.
I mean, the thing about the Torelli group is that even Meyer's theorem says that if you're in the Torelli
Oh, yeah,
group, you
you
get
do,
signature
definitely,
zero.
yeah.
Yeah.
There's lots of ways to see this.
Questions for Dave?
So Drive has a one cochain on the symplectic group such whose co-boundary is this Meyer cocycle mod 4.
Okay.
And I wonder whether you have tried to see what that means if you now.
So I'm sort of dividing Meyer's cocycle by 4 before I even start. I'm dividing the cohomology class by
The
4
cohomology class, yes, but
before I even reduce
cocycle
mod
is
2.
of course not divisible
So-
by 4.
So I mean, what you could try and do is look at the cohomology of this finite group with coefficients in Z mod 8.
Yes.
And the answer is still Z mod 2, but the 4 and the 0, is what I mean. And so the cocycle that one might try and write down may not be values 4 and 0. It may have other values, but then it...
Yes, but if you now connect it with Derive's cocycles,
Yes,
you might get something which has values 4 or 8,
yes.
and then this might be sort of closely related to what you are doing.
Yes, the intermediate term is the brown curve there.
Yes, that's right. Yes, we're actually trying to...
We're doing this
Well,
still work.
yes, exactly. That's work in progress. That's right.
But there is a
So,
hidden here.
so Ed Brown's theorem says that if you look at quadratic forms on Z2 vector spaces with values in Z mod 4,
Exactly.
the width group of them is Z mod 8.
Yes.
And somehow that's the target for the cocycle.
Exactly.
Yes.
So we do know a bit more, but there's plenty here already.
Yeah. I could barely get through this in 3/4 of an hour. So.
Any more questions? If not, let's thank Dave once again.